Muito bom dia, então pessoal, sejam todos bem-vindos. Nós temos hoje uma apresentação do trabalho que foi desenvolvido pelo Timon Benz aqui no nosso laboratório. Timon vem da Universidade de Ruhr, na Alemanha, e esse aqui é o diploma Bachelor Thesis dele, que tem esse título, Ultraviolet Fluorescence Image Analysis as Inspection Method for Photovoltaic Cells. Então o Timon passou alguns meses conosco aqui e está concluindo o trabalho dele. Hoje ele se despede de nós com essa apresentação, esse seminário. Então, Timon, foi uma satisfação receber você no nosso laboratório. Espero que você tenha aproveitado muito. E agora com você a palavra, então, por favor.
Muito obrigado pela introdução. Bom dia também por minha parte. E daqui a pouco vou falar em inglês, vou fazer a palestra em inglês, mas por favor, fiquem à vontade de fazer perguntas em português. Então, voilà. So, the title has already announced this UVF, Ultraviolet Image Analysis, as an inspection method for photovoltaic cells, really for cells in the field, but we're going to come to all that in a second. So, first of all, I would like to briefly introduce myself. My name is Timon Benz. I'm from Essen in the west of Germany, and with this work I'm finishing my bachelor studies that I've done at the Hochschule Ruhr-West, University of Applied Science in North Rhine-Westphalia in Germany. My undergraduate program is called Energy and Environmental Engineering, and the emphasis of my studies have been always on renewable energy, smart applications such as neural networks, and I'm very much into international research, obviously, and collaboration. So that was also, of course, the driving force for me to get here. I believe that in sustainable technology, we do have a global challenge, a global mission, and if we collaborate, we can boost each other's efficiency. So at the bottom left, we have an image of my campus, our campus, in Bottrop, and on the right, you can see myself taking a UVF picture at Tubarão, here in Santa Catarina in Brazil. So as for the structure of this presentation, first of all, I would like to explain to you what ultraviolet fluorescence is, how it creates different patterns, how different parameters influence the pattern. I'm going to define somehow the scope of this work, and I'm going to come to how can we create an experimental setup for acquiring images, and afterwards the emphasis will lie on how to process automatically these images. So first of all, what is UVF? What is ultraviolet fluorescence? If we have a look at the cross-section of a PV cell inside a PV module, we first have the glass at the top, the EVA, ethylene vinyl acetate, the polymeric encapsulant, which is on top and at the bottom laminated to the cell itself and prevents moisture entrance normally. And after that we have the backsheet. As shown in this flowchart, as sunlight enters through the transparent layers at the top, this sunlight degrades over the weeks, months of operation, the front EVA. And this EVA degradation creates degradation products that can fluoresce once they are excited with UV light. And this is the effect that creates the somehow green, yellowish light that we can see here. There is another effect that is superimposed. By this effect is oxygen enters through cell cracks and through the slots between two cells, between two neighboring cells, and this presence of oxygen extinguishes the UVF signal. So the degradation products are still there, but their light, this fluorescing light, is extinguished, and that's why we cannot see any UVF light at the borders and on top of this cell crack. So when I talk about the light, I'll always talk about the UVF signal. And when I talk about this extinguishing process, I'll always call it photobleaking. So I'm going to briefly get over that. So we do shoot photos normally at night to not have the sunlight spectrum, but only the UV spectrum of our excitation source. We can differentiate old and new cracks, and it is important to notice that you should use eye protection. And basically this flowchart is very similar to the previous one, so I'll just skip this. How does it look like in practice? How can I take UVF images outside on the field? So in the simplest case, you could pick one of the UV flashlights. I've got some over here. And You could take them to the field, wear eye protecting glasses, and then you get some images like these. You could also use such a portable UVA inspection lamp, which has somehow a broader light beam, but they are difficult to purchase. The spectrum of the excitation light should be between 360 and 400 nanometers, so really UV spectrum. Just to illustrate the process, how does this look like? How do I interpret a UVF pattern that I get? So at a newly installed module, there is no fluorescence, because it hasn't yet been exposed for enough time to sunlight. Over weeks and months of exposure to sunlight, oxygen, and moisture entrance maybe, you will be able to observe this square pattern. And if during that period cracks or leakages, small cell defects have been produced, you'll be able to see images like these. So on top of leakages, cell cracks, and so on, there is photobleaking, and so at these points the square pattern is interrupted. So we did that. We took our flashlights, UV lights, went to the field and took a lot of images. Which patterns did we observe? Of course, the square pattern, another one which is the ring pattern, different intensities of the square pattern, cracked front glass, some cells with or without UVF, which somehow was very funny to observe, and it's difficult to interpret that. Circular leakages, busbar corrosion along the bus bars here, and cracks through one cell or also over several cells. So the big question is, of course, why do we observe these patterns? Why do they look as they do? And that's a difficult question. I will still owe you an answer to that today, because we still need ongoing research for that. I can, however, say which parameters are influencing. Of course, climate and environment, the module composition, which glass do we have, which encapsulant is present, which additives have been added, and so on. And of course, the whole module handling, as this module handling and installation can cause cracks that, of course, influences the pattern. Now, the difficulty is that the different degradation mechanisms are superimposed. They happen at the same time. And they all affect at the same time the UVF pattern. And they interact. So it's difficult to separate them unless you do lab experiments. So to really explore this, we need ongoing research. For example, time series of UVF images of the same cell. And if you do not want to wait 20 years of module lifetime, you could do accelerated stress testing in the lab, for example, using a heat chamber or illuminating with very high illumination power one cell. And of course, you could use different inspection methods such as electroluminescence, photoluminescence, thermography, in addition to UVF, or also IU curve measurements to really find out what happens within the cell. And of course, there is microscopy, chemical analysis, and so on. So just to give you an insight into how rich the variety of UVF patterns is, these pictures were taken by Mr. Gilliland from the MIT in the United States, from different modules, from different sites and different climate zones. And there is a rich variety, which I cannot cover in this seminar today. But as I marked here, the manufacturer, subtype, and number of years of sun, so the UV dose, basically, is what matters on, what influences the UVF pattern. So what am I going to focus on in my work? I'm going to focus on the square pattern, on the somehow binary decision which cell has a defect, yes or no, and if possible, on the classification, so which cell has which defect. And of course, I'm going to try and process as many images as possible, and as they are different from each other, from different angles and perspective, I try to create something that can process diverse images. So the aim is to develop both an experimental setup and a processing workflow, so software to process the images as automatized as possible to do defect detection. As for the setup, I would like to keep it simple and efficient with low costs and easy to purchase so that everyone who owns a PV power plant or some modules could easily purchase that and use it. And as for the criteria of the processing tool, it should be, of course, automatized to save work time and save work hours. It should be efficient, generalized, and user-friendly so that it's really suited for use, for commercial use maybe in the end. So let's start with experimental setups. A group of researchers, I'm going really quickly, a group of researchers in the north of Germany developed this hood structure in 2017. On top of that hood, there are UV lights and the camera. And the hood is there, of course, to block sunlight so that you can take UVF measurements even during daylight. However, this structure is quite heavy. It weighs 12 kilos, and the person there wears a backpack. Inside that backpack, there is a battery to supply electricity to the UV lights and maybe to the camera. And passing this structure from module to module, you can take around 200 modules per hour. An alternative possibility would be to use this handheld inspection lamp. I would have liked to get one of these, but they are difficult to get. There are no producers and very few sellers at the current moment in Brazil. In Europe and the US, it's somehow easier to get one of these lamps, but still you would need to import them to Brazil and they might get stuck at customs. So due to logistical reasons, it's difficult to get one of these. So in my project, I used flashlights. And yeah, costs would be between $20 and $50 for that. Maybe the most efficient method that I have found in literature was developed by a team of researchers around Mr. Gilliland from the MIT in the United States in 2019. So they used a monopod attached to a backpack structure so that it doesn't result that heavy, so that it's stable. This monopod is 5 meters high. On top of that, there is a professional camera flash. The filter in front of the flash has been altered so that you really have UV light coming from the flash. And likewise, you can illuminate 4 to 5 modules at a time, shoot an image of 4 to 5 modules. And if there are 2 rows of modules, you can process 2,000 modules per hour. If there's only 1 row, they are saying that you can process 1,000 modules per hour. So I started very, very simple. I just took 2 flashlights, the one that I've shown, attached them to a tripod, and took this structure to take already some images of some cells. We ordered more flashlights because illumination power wasn't enough, and step by step we added these flashlights to a metal structure that I've mounted on top of the tripod. And in the end we had 7 to 9 flashlights. Some of them had a somewhat awkward light spectrum, different intensities, and so on. So I used around 7, which are 250 LEDs approximately, and would cost around $70 to $90. Of course, depending on which tripod you want to use, whether the tripod is already present or not. In this whole view on setups, I'm not talking much about cameras. The reason is that it worked fine already with my smartphone camera. So I suppose in each photovoltaic laboratory, everyone who owns a PV plant already has a smartphone, and that for the beginning you could also use a smartphone. In literature you'll find a lot about which camera is used and which filter is used. So what about the future? Which is the tendency? Which setup are we going to use in the future? If we follow this evolutions towards higher throughputs and more automatized workflows, we might expect drones to be used in the future. And there are a lot of criteria that you need for this application. So it would need to be a commercialized, inexpensive drone that anyone could fly without a lot of instructions. It should have a certain stability so that if you use an exposure time of 0.1 seconds, if you use a relatively large exposure time, that the image still isn't blurred. And there is a lot of energy demand, so this drone would need to carry its own weight, the camera, the UV light, and a battery that supplies enough power for all of that. So probably flight time would be quite reduced, and you would need another battery on the ground to change batteries and so on. And you would have probably a few minutes to up to maybe 10, 12 minutes of flight time if you're really optimizing it quite a lot. I'm just estimating. And even if you manage to buy all that equipment with the somewhat elevated price, you still need to do a physical compromise between resolution per cell and how many modules you cover at a time. If you flow very low, you get good resolution for each cell image in the end. but you do not cover a lot of modules. On the other hand, if you fly very high, you can cover a lot of modules, but the resolution for each cell obviously will be very low, and the quality of the classification of defect detection will of course suffer by that. So to compare, I think that three main criteria and parameters are very important: price, illumination power, and the throughput. So I listed all that. With rising price, you can buy more illumination power, which I think is very much worth the effort. And you get a higher throughput because you can illuminate more cells, more modules at a time. And then in the end, it's somewhat the question whether you want to use a handheld setup or a drone, which I'm not going to answer right now because it depends on the situation, on the size of the PV plant, and so on. Okay, so this serves as an overview, as a discussion, as an aid for decision making, which setup you want to use. Then, once you have chosen your setup and acquired a lot of images, you will want to process them in an automatized way. And I had a look at which processing tools are available on the internet, and I found OpenUVF, which was developed by Mr. Gilliland, the one who developed this monopod structure 5 meters high and so on. And they were, so here you can see they are taking images of 4 to 5 modules at a time. These are the images acquired with the monopod. They are first binarizing, merging cells together, then merging cells to modules, detecting module contours, doing perspective transformation on each module image. And then we are at this step 5. They crop each cell out and pass it through a TensorFlow model that does object detection on cracks, so only on cracks. And this object detection can predict where a crack is and with which probability. So for example, 99% probability in this case. The problem of this tool for me was that it was difficult to install. It is freely available on GitHub, you can try yourselves. But for me it was difficult to install, and it is directly written in TensorFlow with commands and functions from TensorFlow, which is difficult to read and difficult to adapt for beginners in deep learning. So honestly, I couldn't adapt it, and I couldn't adapt it to my image processing. So I started to develop a new processing tool, which is written in Python and uses OpenCV. OpenCV is an image processing and deep learning library and stands for Open Computer Vision. So the first step of my own tool would be to construct a pipeline that processes a module image with the aim to get the module contour in order to then be able to do perspective correction on the module image. And this of course needs to first erase connections between cells and the module frame to get a clear shape of the module. So I started to apply brightness correction because the illumination with my flashlights wasn't homogeneous enough. I used the gamma method and color histogram equalization for that. And afterwards, I converted to grayscale or only used the green color channel. Why only the green color channel? Well, I splitted this image into color channels and observed an interesting phenomenon. So when we have our flashlight and the UV light hits the surface of the module, I suppose that a part of this light spectrum, blue light spectrum, is directly reflected and comes back into the camera. That is what we can see in this blue color channel. The part of the light that is absorbed by the degraded products and re-emitted has less energy, so reduced wavelength, and likewise it falls within the green color spectrum. That's why we can see very clearly the UVF spectrum on the green color channel. And as for the red light and red color channel, I suppose that's stray light, ambient light, and to be honest, when I shot that image, I shot it right outside the laboratory here. There was a somewhat yellowish-orange light source behind me, and that's why you can see very clearly my own shadow on the second module there. So this, of course, helps to really separate, to get the UVF pattern very clearly, and to get sharp edges of the cells. So after that, I inverted the image. That has to do with that we need to define what is the background, what is the foreground. In OpenCV, white objects are the foreground, black objects are the background. And this grayscale image has values between 0 and 255. And for contour detection, we need a binary image, a black-white image, that only has pixel values of 0 or 255, so only 2 pixel values. And I applied simple thresholding. There are other thresholding techniques that, like Otsu's method, Kenny edge detection, adaptive thresholding that uses a local average and so on. However, these methods generated an image that was too rich of information for me to process. And this simple thresholding, just taking, for example, 150 as a thresh, is simplifying a lot and served in my case, so I just used that. So, as I said, on this image you can already do contour detection, and you get a lot of contours, usually between 1,000 and 3,000 contours, external contours only, which is a lot. And actually we want only one contour, the module contour, and we need to get rid of the noise. There are a lot of contours that are very short, very small, around noise. So we want noise reduction. We can get that by applying morphological operations, such as dilating, filtering, and there are even others. I used only these two. So dilating means to increase white areas. Median blur is a filter that filters out salt and pepper noise. And if you increase the kernel size, it filters out any noise that is smaller than the kernel size. So for example, 3 times 3 pixels, 5 times 5, 7 times 7, and so on. After these two morphological operations, I applied once more contour detection on external contours in order to monitor how complicated the image still is, how many contours there are still. And I stopped that whole loop of morphological operations once we have less than 100 contours, or less than 20 iterations if the contours aren't decreased quickly enough. So this criteria of less than 100 contours assures a certain simplicity of the image. And I didn't go further, because if you go further, you run the risk of merging two modules together, and then basically you destroy your module contour. So for example, in the step of crossing less than 100 contours, we get 76 contours, and we cannot continue there. So we need to filter these contours, and luckily OpenCV allows us access to the contour properties, and we can use these properties by selecting exactly the contours that we want to have. And I want to have the module contour, which shall have 4 corners, which is, in all of the cases, between 20 and 95% of the image. It won't be a very small contour. And I claimed in conditions C and D that opposite sides shall look in the same direction and approximately have the same length. And in the end, of all of the contours that fulfill conditions A to D, I chose the largest contour, which worked for me to get the contour of the module. So let's dive a bit into the criteria C and into the criteria C. How did I do that, or how do we handle contours? If you just perform contour detection, you get a very large list of thousands of points, and each pixel, each point that defines the contour is one entry into the list. That's very difficult to process. OpenCV allows you to simplify, and likewise you can approximate the contour and get only hundreds of points. That helps a bit, but still it's not very easy to handle. Then you can do this polynomial approximation function to approximate, and this serves very well for geometrical contours, so parallelograms, trapezoids, triangles, or in this case a rectangle, or distorted rectangles. However, this polynomial approximation needs a certain tolerance, which is called epsilon, and that's an important parameter. The influence of that parameter is demonstrated here. So if we have that original image, perform contour detection and approximation, and we have a very low tolerance, then the contour follows these triangular disturbances. And we have an approximated contour that is very close to the real contour. However, if we allow a higher tolerance, a higher epsilon, we get a more geometrical contour that can differ more from the original contour. And this is, in this case, what we want, of course. We want this rectangular shape. In the next slide, I'm going to show you a case in which this goes wrong. So, as for the parallel side length criterion, how did I it's only about the direction, parallel sides. How did I implicate that? First of all, to identify the corners, I built the sum of x and y coordinate, which is minimum in the top left and maximum in the bottom right. And then you can identify by comparing x and y values all of the four corners. So you know which is which. Then, knowing which is which, I computed vectors for each side and converted them to polar coordinates. And I compared, for example, this beta 1 and beta 2, these angles that are with respect to the positive x direction. And if these two angles are more or less equal, the sides C and D, C and A, will be parallel, more or less. So I calculated the angular difference between these two in degrees. And if this angular difference is lower than a certain tolerance, a certain thresh, I allowed that contour and did perspective correction. To demonstrate that that works, I wrote this small demonstration program. I synthetically created a row of trapezoids with different inclinations, different angular differences. I performed contour detection, contour approximation with an intermediate epsilon. And you can see here that the first contour has been approximated as a triangle, so not as a trapezoid. And as in the next step, I claim the contour to have four corners. This first one is already discarded. The last one has been, purposely, cut by the edge of the image. And this contour has 6 points, because it goes all around the inside and the outside of this U-shaped white area. So it has 6 points, and it's also discarded. The other three ones are allowed at an angular tolerance of 40 degrees. If we decrease this tolerance, only these two ones are allowed. At 20 degrees, only this one is allowed. At 10 degrees, none of these is allowed. So to pass 10 degrees of angular tolerance, you would really need a perfect parallelogram or nearly perfect parallelogram. So it worked for me. I got the module contour, the four corner points, and that's what I wanted. Because likewise, I can do perspective transformation. I calculated average width and average height, got the target size, and using functions from OpenCV, I can compute a transformation matrix, apply this transformation matrix, and I get the perspective corrected module image. So that was already the first main pipeline, the first main script that I developed. And this is the summary of everything done in this script. So the second step would be departing from this perspective-corrected module image to crop single cell images, both on the binary image and on the original image for later processing and decision-making. And actually, I applied the same pre-processing operations. I just altered the morphological operations loop and the contour filtering conditions, because the cell contours are different than the module contour. And I also integrated these checks of contour conditions within this loop. So earlier I had it outside the loop, now I'm doing it inside the loop to monitor exactly how many cells we have. So which are the contour conditions for cells? Obviously they are squares, so each side length should be equal to the other three. And they have four corners. And if one module is composed of 60 cells, I can say that the area of the cell contour should be approximately 1/60 of the module area, which is the whole image area in my case, approximately. And if that's fulfilled, I allow the contour as a cell contour. So for example, I got 113 contours here, of which 40 were true cell contours. And as an abortion criteria for this loop, I monitor the number of cell contours, and if that decreases, so if we have just destroyed one cell contour, I use the previous list of contours and use this list for cropping the cell images. At first I thought it would be nice to extrapolate a grid in order to also use these cells at the edges, But at the second thought, I thought better of it, because they are outside the light beam of my flashlight, so they have a bad illumination and likewise a bad image quality, and they do not contribute a lot of information for my decision-making process. So the third and last step would be to use a CNN, a convolutional neural network, to classify the cell images that I've just cropped. So here we have the cell images, our convolutional neural network, and in the end we would make the decision which one has a defect, which one hasn't. And I definitely recommend to use Keras, which is quite handy and user-friendly. So first, I'm going to introduce you to the basics of neural networks. Afterwards, talk a bit about convolutions and convolutional neural networks, which can be used for image processing. And in the end, we're going to have a look at how you can do image classification with CNNs. So, actually, where did this idea come from to do neural networks? It is inspired by biology. There is a certain similarity in the working scheme of biological neurons and neurons in computer science. So as the input or the dendrites of the neuron are connected to a lot of others, signals reach this input spot and they are summed up, or a weighted sum, if you want so. And if this sum is higher than a certain threshold, it can be a thresholding function, also called activation function, then a proportional output is passed to the neighboring neuron, or to the neurons that are connected to the output. And we can sum all this up in three main aspects: the sum at the input, a thresholding or an activation function, and a proportional output. And if, just for starting, we only consider one neuron and we leave aside the thresholding for later and focus on this proportional output, a neuron can just be moduled by a simple multiplication. So the output value is the input value times the weight. And of course, in networks of neurons, the question is which operations can we use for that in case of more values. So if you have three input values, three output values, and you have a fully connected layer, so each input is connected to each output, you could calculate this multiplication step by multiplying the input vector by a weight matrix to get the output vector. And this is already our very first fully connected layer. Then you got these output values. They are the predicted values. And we want to teach something to the neural network. And because we're in supervised learning. In order to do so, we need to compare the prediction to the reality. We need to compare output values to the so-called target values, or I named them goal in the slides. So we need to quantify this difference. We could of course use just the deviation, the simple subtraction of output minus goal, but there we have a sign problem if that gets negative, and usually we always use the squared error, so output minus goal squared. And if we remember how we created this output, multiplication of input times weight, we can substitute. And we can substitute this inside our error function, and we get a function, error, depending on the weight, which is a quadratic function, a parabolic function. So we can plot it like this. And let's suppose that our current weight value, at the beginning they are randomly initialized, lies here. And the current, the current error is here. We of course want to reduce the error. So we want to get to this optimal weight position. And we need some information on how to get there. We can get this information from the first derivative, from the slope of this line. And practically in this algorithm, I'm not going to go through each step, we are subtracting the slope from the current weight position. So we are here, we want to go more right, the slope is negative, current weight minus the slope adds something to the weight increases, and we get more to the right. And likewise, step by step, we get to or close to this perfect weight position. Just to imagine this better, imagine you're somewhere up the mountains, somewhere up a hill at night or when there is fog, and you want to get to the valley, back home somehow, and you cannot see far. But you can feel the slope underneath your feet, and you can try to go into the direction where it goes down most, similar to water flowing down a mountainside. And this is ideally what we would want to do in this algorithm. This algorithm is called gradient descent algorithm because we're descending and we're using the gradient as information on in which direction to go. And this algorithm can optimize the weight value once we have an error for each neuron. So this is what we need. And within a network of several layers, we would first do forward propagation. So step-by-step multiply input vector times weight matrix, once more vector times the second weight matrix, and so on until we reach the output layer. Then we would compare each output value to the target values, create the error signal, and now we have an error for each of these last connections, but we do not have an error for the second last, third last, and so on layer. Oops. And we need to assign one error value to each neuron in order to do the gradient descent method. So we propagate backwards by multiplying the error vector times the transposed weight matrix, which propagates backwards the error signal. And then we are adapting the weights. Doing this step by step on each sample that you have of your data, you can learn a data set. You can learn the correlation between input data and target data and get as close as possible to that. And these layers are called fully connected layers. So how could you code that? How could you start your own deep learning application? I would definitely recommend to use Python, Keras, TensorFlow, and the IDE you prefer. So Keras is the front-end library that is user-friendly for beginners. TensorFlow is the back-end library that takes care of accelerating matrix times matrix or tensor times tensor multiplications to have high computational speed. And you can of course use your IDE that you prefer. I'm using PyCharm, for example. So how can we process images as input data for neural networks? We need some operation that preprocesses and simplifies images and gets features, characteristical features out of these images. And this operation could be the convolutional operation. It is. Convolution is an image filter, a kernel matrix that is passed step by step, line by line over the input matrix, the input image at the first step. And the result is stored in the so-called output feature map. You use usually 32 to 64 filters for each sample. So you're creating 32 to 64 output feature maps and a lot of data. We need to select the most important features, the most important values, which are the maximum values. And we get these by applying max pooling. And max pooling layers are in between convolutional layers to select maximum features. So how would this look like practically? For example, if we would want to classify a dog, the first convolutional layers, the first filters, would detect very small scale features, for example, horizontal edges, vertical edges, tilted edges, and so on, or textures, for example, structures. And so it continues. These small features merge together to larger features until you get features that cover the whole image and describe, in the best case, very well the dog. For example, body size, the white fur, and so on. And these features that are really important for our classification, you can pass them into the classifier, which consists of two fully connected layers at the very end of the network. And then you can do the predictions that you want. So how would it look like to build up? How looks the architecture of a CNN for image classification? This is the very popular MNIST dataset example. You would want to classify digits and determine handwritten digits. So you would have a stack of convolutional layers and max pooling layers stacked one over each other. There are a lot of tensors involved, and you need compatible operations to the tensor sizes and so on, that it works well together. Likewise, you're extracting the features. These features are handed into the fully connected layers, which form the classifier, and you have as many output neurons as you have output classes. So in our example, exactly 10. So from 0 to 9, each digit. And you would get as an output the probability that this input image belongs to the class. So ideally, 0, 0, and 100% for 2, and then from 3 to 9, 0. So as a summary on this part on neural networks and convolutional layers, we first had a look at single neurons, single layers, fully connected layers. They make predictions by multiplying the input times the weight, and sometimes check whether there is, whether the input is higher than a certain threshold. In order to learn, in order to teach something to the network, or to a single neuron at the beginning, we use the gradient descent method by using the error, the derivative of the error. In case we have several dimensions, the derivative becomes the gradient. And likewise, we can adapt the weights step by step. If we have a deep neural network of several layers, we first need to do forward propagation to get an output, get the error signal, do backwards propagation of the error signal, and then we can do for each neuron the gradient descent method. And in the end, for classification, you would use convolutions and max pooling layers at the beginning, and then add a classifier, typically 2 fully connected layers in the end. Okay, so to summarize it all up, this would be, in images, the whole workflow of the tool that I'm proposing, that I'm developing right now. The first 2 pipelines are using a lot of functions from OpenCV to get the module contour, module, a perspective-corrected module image, and then from this perspective-corrected image, do another morphological loop and so on, filter contours to crop single-cell images. And in the end, all this part about image classification using convolutional neural networks. So before I stop this presentation, I would like to give my special thanks to Professor Ricardo Rüther. Thank you very much for welcoming me. Thanks for the thanks for the introduction, and thanks for taking care of all the formalities. Same for my German professor, who's not here right now, Professor Markus Rehm, who also proposed the contact and helped me to get here and to get over all the formalities. Thank you, Aline Kirsten. Thank you very much for all the support. You had always a helping hand for me and some orientation, which was very useful and helped a lot. And of course, also thanks to the employees of the international offices of my university, HLW, Hochschule Ruhr-West, University of Applied Science, and also to the employees of the international office of the UFSC, Universidade Federal de Santa Catarina. They helped me to get through all the processes and to really get here in person. It has been an amazing atmosphere. So thanks to the whole team. Muito obrigado para vocês. Vocês são uma equipe genial, uma ótima equipe. Foi muito legal. E agradeço a sua atenção. So thank you very much for your attention. I leave you my email address and my contact. So yeah, I'm at your disposal for questions right now. Thank you.